Alright, so welcome back. It's been a much longer break for me, so I had to reconstruct the values that we had before. For our transect, we had 5 quadrats. The average number of individuals within each quadrat was 1.8, and the variance, the variation, right, the variability in these quadrats as determined by the variance was 2.2, and that gave us a particular variance to mean ratio of 1.2. And then I said that these variance to mean ratios can either be greater than 1 or less than 1, or not significantly different from 1. So what we need to do is apply a statistical test to figure out whether in fact the variance to mean ratio is different from 1 significantly, and if it is, we can use the numerical value of the variance to mean ratio to determine whether in fact it's larger or smaller than 1. Okay, so to do this, we need to use what's called a chi-square. Some of you have a lot of familiarity with chi-square. It's typically from genetics, also I think covered in descriptive statistics. So let's go ahead and calculate one of those. So, don't need this anymore, but we will need the chi-square calculation itself. I have this up here. It's the sum of the observed minus expected squared over expected. Okay? So, the average value in each quadrat is really the expected value. So even though along my transect I have 4, 2, 2, 0, and 1, the expected value in each of these quadrats would be 1.8, the average value. What I observe are the actual measurements that I took. What I expect is the average. So the observed would be the individual value for each quadrat, and the expected then becomes the 1.8 value. So here, that gives us a chain of measurements that we're going to have to sum up to get the chi-square value itself. All right, so we start with the first quadrat. The observed minus expected would be 4 minus 1.8 over 1.8, right? Plus, could do it this way, 2 times 2 minus 1.8 squared over 1.8, do it 0. Finally, the 1. 1 minus 1 squared. Right, now I've been running around like a chicken with my head cut off. I gave my first exam in AFF. I used Blackboard, and I'm still dealing with some of the fallout from that. So, like an idiot, I didn't do this calculation out first. So, let's go ahead and work that out. I think I have Excel here. That should be able to give us these values. So if I do them as equals All right, so that value squared divided by 1.8 equals 5, divided by 1.8 equals 0.02. There are two of those. 0.24 divided by 1.8 makes sense. And that would give us the overall chi-square value of 7.2. Now, I do this as chi-square calculated. That's the chi-square value that was calculated from our data. Okay? Then what we'll do is what's called a chi-square critical. And in these distributions, like the chi-square distribution, chi-square distribution looks a bit like this. And these are the chi-square values that are possible, and somewhere in here is this chi-square critical value. That value marks the point at which 5% of the distribution is above this critical value, 95% is below that critical value. So in stats class, what you probably did was figure out what this critical value was and then compared your calculated to your critical value. If your calculated value is larger than your critical value, that means for us that this variance to mean ratio is significantly different from 1. And if it's less than this critical value, it's not significantly different from 1. From a statistical standpoint, the overall hypothesis that we're testing is the null hypothesis that the variance to mean ratio is equal to 1. And then we have two alternatives, alternative 1 and alternative 2. Alternative 1 is that the variance to mean ratio is greater than 1, and alternative 2 is that the variance to mean ratio is less than 1. So if our calculated value is greater than our critical value, then we would reject the null hypothesis. And if the calculated value is less than the critical value, then we would fail to reject. If we reject the null hypothesis, then one of the two alternatives is correct. And if we fail to reject the null hypothesis, then the variance to mean ratio is not different enough from 1 to be considered statistically different from 1. Okay? Now, in my day, you'd have to look these critical values up in tables. And there are an infinite number of these chi-square distributions. The distribution you want is the distribution based on your data. So we had 5 quadrats that we looked at. And what we need to do is calculate out what are called the degrees of freedom. And the degrees of freedom are equal to n minus 1. So in our case, our distribution has 4 degrees of freedom. So you'd look up in the table the chi-square distribution for 4 degrees of freedom. You would get the critical value for the 5%, and then you would compare these two. But in the modern age here, computers can very quickly calculate out these distributions very easily. So what we're going to do then is take our chi-square calculated, that goes here, and our chi-square calculated was 7.2, and the degrees of freedom here that we have are 4. And a chi-square calculated of 7.2 and a degrees of freedom of 4 gives us a p-value of 0.1257. A p-value of 0.05 or less would indicate that the calculated was above the critical value, allowing us to reject the null hypothesis. Instead, the p-value is greater than 0.05, which means our value here that's calculated of 7.2 is somewhere to the left of this. This tells us that the variance to mean ratio was not significantly different from 1. We failed to reject the null hypothesis. And this tells us that the dispersion of our organisms in space is what we would call random. Okay? All right. Now, for objects in space, or in our case, organisms, we expect typical kinds of dispersions based on how organisms interact with each other. So, if our organisms are social, right, they like to hang out in groups, then I would suspect that my organism has a clumped distribution, right? Zebras have clumped distributions. Meerkats, right? Prairie gophers, they have clumped distributions because they're social animals. They tend to live together in groups. On the other hand, there are some organisms that tend to be fairly solitary. There are a number of solitary bees, right? They build little nests underground. My expectation is that if these nests are arrayed in space where these organisms are living, that I would expect a fairly uniform distribution. I would expect a similar thing with plants like trees over time. I mean, initially, I might expect that a bunch of acorns were distributed in a particular place because a squirrel put them there. And early on, these seedlings would have a fairly clumped distribution. And they would be fairly clumped because that's where the seeds were put by the squirrel. Over time, as competitive interactions start to occur among all of these seedlings, my expectation is that we would move toward a more kind of uniform distribution, as there are certain distances that these oak trees tend to be apart from each other when they get to be fairly large. They're shading out the organisms underneath them, and the competitive interactions between two trees here, a very intense form of competition. Somebody's going to win and somebody's going to lose. So we might expect the movement of this distribution from a more clumped distribution over time through competitive interactions to a more uniform distribution. Okay? I keep saying distribution. Uniform dispersion is probably a better way to put it. Okay? All right, now, this idea of dispersion also comes to play when we talk about parasite-host interactions. So let's take a particular pathogen here, a particular type of parasite. Let's make it an intracellular parasite, right, a little pathogen. And let's make it one that causes a particular disease in plants. There are a few of them here that we could talk about, but let's just take Dutch elm. That's one people talk about a lot. This pathogen of Dutch elm needs to be able to move between trees. it needs to be able to be moved from one host to another host in space. The probability of being able to do this is based on the distances apart that these trees are. So my expectation is if I had a particular woodland here and a lot of Dutch elms very close together, that if one of these trees became infected, it would be fairly easy for the pathogen here to move between trees, right? Because its ability to move is based on the distance apart that these individual trees are. Okay? All right, so if we started out with these Dutch elms, in the 40s and 50s, these things were everywhere. I mean, the idea of elms being in every town is exemplified by the fact that every town has an elm street. And at one point, elms were very, very common trees. They were used in cities because they're very straight-growing trees. They don't have a lot of lower branches. So they work pretty well for those boulevards and alleys where cars can drive under them, trucks can drive under them. And they're very stately-looking trees, very nice-looking trees. So the elms were planted everywhere, all over the place in towns. And then along came this pathogen that causes Dutch elm disease. And over time, what the Dutch elm pathogen did was take a dispersion of Dutch elm that was fairly clumped, right? Lots of them